Hello everybody and welcome back to Calculus. This is the second part of the video lecture about continuity. So this is part 2 when we're going to talk about continuity over some intervals, and here the main goal of all of the problems really will be to find the domain of each function. Okay, so let's just go ahead and jump right into doing these problems. The first problem says I have a function f of x is equal to 3x plus 1 over x squared minus 25. So this is a rational function where the only issue that we might have is in the denominator. So to find the domain, we'll say x squared minus 25 can be equal to 0. So that means x is not equal to plus or minus 5. So if you were to graph the domain, you would exclude these two values, right? And everything else is okay. All right, so this rational function is continuous everywhere except negative 5 and 5. Okay, so the interval would be from negative infinity to negative 5, union negative 5 to 5, union 5 to positive infinity. Okay, all right. Let's take a look at the next rational function. Here we have 4x plus 1 over x cubed minus 9x. Let me go ahead and factor this. 4x plus 1 over x. This would be x squared minus 9. So I can factor it even more. This is x times x minus 3. X plus 3. Okay, so 3 points would be excluded from the domain. 0 is one of them, negative 3, positive 3. I have 4 intervals, okay, from negative infinity to negative 3, not including the endpoints, right? From from negative 3 to 0. And then from 0 to positive 3, union, and 3 to positive infinity. Okay, so on the left here you have a graphical representation of the domain. On the right we have the interval notation, so the function is continuous on these intervals. Okay, it is continuous on its domain. Just like in the previous example, these are the intervals where the function is continuous. Okay, you might be asking, is it always going to be the case for rational functions that we have some points that are excluded? Well, this next example tells us no. If you take a look at this expression right here, this is a rational function with a linear term in the numerator and a quadratic in the denominator, but x squared plus 4 is never equal to 0 for real numbers, right? Okay, for complex, yes, it can be, but we're not dealing with complex numbers. We're dealing with real valued functions. So if the denominator is never 0, then the domain is all real numbers. And then we say that this function is continuous everywhere. Okay, so this function is continuous for all x. Okay. Every one of these values will be fine. All right, so rational functions. Find the points that make the denominator 0, if there are any, exclude them, and we're good to go. Radical functions, let's take a look at those. We've done similar examples. So we need to take the expression under the radical and set it to be greater than or equal to 0. So start for x. Okay, so graphically, what does that look like? This point we include because we can have a 0 under the radical, no issue there. Okay, so the function is continuous on which interval? We go from 7 over 4, including the endpoints, hence I have my square bracket here, to positive infinity. Okay, So any other point we will have discontinuity. So you can always check. Okay, let's say I plug in a number that's to the left of 7 over 4. Let's just plug in 1. 4 times 1. Okay, 4 times 1 minus 7. Square root of that is undefined. Okay, that function is not defined for x is equal to 1. Hence, it's discontinuous. Okay, there is no point to talk about continuity unless the function is defined at that point. All right, next function, we have a radical expression with a quadratic expression under the radical. Okay, let's see how we deal with these. Still, this is a square root. We need everything to be greater than or equal to 0. Okay, let's solve for x. So this is x squared. I'm going to write that negative here. So what is this? This x squared is greater than or equal to 4. And remember, this is inequality. This is not an equation. So negative 2, positive 2, those are the two values that will split our domain. And the question is, which of the subintervals are in the domain? So you can actually plug in numbers from each of the intervals to check. So let's say I plug in 0. That's between negative 2 and positive 2. 0 squared, like this, 0 squared, is that greater than or equal to 4? No. Okay, so we're going to pick values that are outside of this interval. Okay, so from negative infinity to negative 2, not including values between negative 2 and positive 2, and then from 2 to positive infinity. You can always check this. Plug in a value from here. So let's say negative 4 squared. That is positive 16. That's greater than 4. Anything from here, let's say 5. 5 squared, that's 25. That's greater than 4. Okay, so the domain is the union of two intervals from negative infinity to negative 2, including union 2 to positive infinity. Okay, so we include this point. And that's when the function is continuous. It is continuous on these two intervals. All right, let's take a look at the cubic root. We have a cubic root of an expression that's also quadratic. Now, as soon as I see a cubic root, okay, which means this expression can be positive or negative, right? So it could be positive or negative. That is okay. Negative, not 0. Okay, which means the domain of this function is all real numbers. The domain is everything, which means f of x is continuous for all x. Okay, any number that we plug in for x will be fine. 0, that's fine. Cubic root of 0 is 0. Let's say we get negative 8. That's okay too. Cubic root of negative 8 is negative 2. Okay, positive, no issues there. So anything that you wish to plug in will be fine. So the function is continuous for all of these x. All right, let's take a look at an expression that has a fraction and a radical. So here we have to be a little bit careful, because now we're going to set our x plus 7 strictly greater than 0. It can no longer be equal to 0, because then we will have division by 0, which is undefined. Okay, so x is greater than negative 7. Negative 7 is somewhere here, so anything to the right of negative 7 will be okay. Anything else to the left of it, that's not okay. That's not in the domain. So this is your domain. From negative 7 to positive infinity. So the function is continuous on the interval from -7, not including, to positive infinity. Again, if you wish, you can always just check. Okay, plug in some numbers. You can plug in 0, that will be okay. 5 over square root of 7, no issue there. That's a number, that's well defined. I plug in -20. -20 plus 7, -13. I cannot take square root of that. Okay, so always check your work if you're not sure. So let's see, what have we done? We've done rational functions where we have discontinuities. Then we've done rational functions when they're defined for all values of x, so that means it's continuous on R, all real numbers. We've done radical functions. We've done radicals with more complicated expressions under the radicals. Then odd roots, okay, so this will be okay. The solution will be similar if you have 5th root, 7th root, 13th root, and so forth. Okay, if it's an odd root, you don't need to worry about the sign under the radical. If it's an even root, yes, we have to worry about this expression needing to be either greater than or equal to 0 if it's not in the denominator. If it is in the denominator, it needs to be strictly greater than 0. Okay? All right. So now we're done with these functions. The next set of functions will be trig, and those are the ones that usually cause most trouble, okay, because you have to remember a lot of rules from trigonometry. Let's take a look at the following example. Determine the points of discontinuity for functions involving trigonometric expression. Okay, I have a function composition here. I have a not radical, I have a fraction with trig functions on top and on the bottom. Okay, so 1 plus sine of x. This function is continuous for all x. Okay, no issues there. We know a sine function is a nice, smooth, continuous function, continuous for every value of x. It just goes forever in each direction. If we add 1, we're just shifting it, but there are no issues there. Now, cosine itself is a continuous function, but because it's in the denominator, we need to make sure cosine x is not equal to 0. When does that happen? Okay, it happens for what values? So that means x is not equal to pi over 2, 3 pi over 2, 5 pi over 2, and so forth, right? You get the idea. All these multiples of pi over 2. So in general, so this is your general formula, okay? We don't want x to be equal to some odd multiple of pi over 2, okay? 2k plus 1, that will give you an odd number, okay? Because if you get an even number, then that 2 and 2 will cancel out. You will get something like 4 pi or 3 pi, 2 pi. But cosine is not equal to 0 at those values. It's either 1 or -1. Okay, so we want to make sure that this guy right here is odd. Okay, so odd multiple of pi over 2. Those are the points of discontinuity of this function. Take a look at the next example. All right, here I have 2 over sine of x minus 1. Same as before. I don't want my denominator to be 0. So sine of x is not equal to 1. When does that happen? Okay, when is x is equal to 1? One angle, pi over 2. X is not equal to pi over 2. Remember, 3 pi over 2, x is equal to -1. -1 is okay because if I have -1 in the denominator, I'm just going to get 2 over -2. No issues there. Okay, so pi over 2, and remember, sine of x is a periodic function. Okay, so we want to make sure that if we add any multiple of 2 pi, then we want to exclude all those values, right? So plus 2 pi k, these are all values that need to go. Okay, think about it as your unit circle, right? So here's your pi over 2 right here. Okay, well, if I add 2 pi and back to that number, that makes the denominator 0. Okay, if I add another 2 pi, okay, so let's say 4 pi, and here I am again. So we want to exclude all of those points to avoid division by 0. All right. Okay, so we've done something with sine, cosine. Let's take a look at tangent. 5x. That function has no problem, right? Okay, continuous for all values of x. Tangent x plus 1. Tangent x plus 1. We don't want that to be 0. So that's tangent x not equal to negative 1. Let me remind you where the tangent is equal to negative 1. Okay, so over here it's 1, right? Second quadrant for this angle, that is where it's equal to negative 1. Third quadrant, sine and cosine here both negative, so we get positive. So here it's positive, here it's positive, here it's negative, and here it's negative. Okay, so we want to exclude what values? Okay, this is 3 pi over 4, and this one is 7 pi over 4. Okay, and any other number such that we come back to it, right? So this is what? This is period of pi. Period of pi. Okay, so we want to exclude. We want to exclude 3 pi over 4, 7 pi over 4, all these values. So in general, how would we write this? Okay? We don't want, so x is not equal to 3 pi over 4 plus a multiple of pi. Okay? That is the points, these are the points of discontinuity. Okay? You can check, plug in any other number. It will be alright. Just use a calculator real quick. Plug in a value for x such that it's not of this form. You'll get some number, you'll get a well-defined number, but you will not get a 0 in the denominator. Okay? Plug in 7 pi over 4 plus, let's say, 3 pi. And you'll see that you can have division by 0. Okay, last example here. Negative 3 secant x. This one is fairly straightforward. You just need to remember with the domain of secant x. Okay? Remember, secant of x is 1 over cosine of x. We don't want cosine to be 0, right? Cosine 0 where? Okay, so we don't want x to be pi over 2, 3 pi over 2, or any multiple of those. Okay, any even multiple of those. Okay, so we don't want that. Alright, this negative 3 doesn't really do anything. That is just stretch, right, and reflection. Okay, so here in general, the points of discontinuity are what? Okay, we don't want x to be pi over 2 times what? Let's do 2 and plus 1, right? Times some odd number. Okay? If it's even, again, let me just show you. If let's say this is an even, what if it's an even number? Even multiple of pi over 2. Let me give you a quick example. So let's say I have 6 times pi over 2. That gives us 3 pi, right? Okay? But cosine of 3 pi, what is it? Okay, it's not 0, right? Okay, cosine of 3 pi, 0, 1, 2, 3. Cosine is negative 1, right? So cosine of 3 pi is negative 1. Okay? So secant is actually defined like that one. Alright, so for these problems, we just need to remember the properties of trig functions: sine and cosine, secant, cosecant, tangent, cotangent. And once you remember the unit circle and which trig functions take values such as 0, those are the ones that we want to avoid, at which numbers, if you remember all of those, then you should be able to solve all of these problems. Alright, thank you for watching.